All right, in this chapter, we're going to talk about probability density functions, specifically regarding continuous variables. So, all right, so first type of probability distribution we're going to talk about is the uniform probability density function. So, y'all might recall back in chapter 3, we talked about the different shapes of distributions, and uniform was one of those four big shapes where all the outcomes were equally likely. So, we're going to look at a probability density function on example 1. And one thing to know is when we are looking at the graphs, we are trying to associate the area under the curve with the probability of the random variable. So the total area under any probability density function must always equal 1, which that's very important. Okay, so on example 1, let's say Professor Collins lectures anywhere from 45 minutes to 60 minutes each class. So we're going to let the random variable x represent the time when I finish lecture, with all equal intervals of time being equally likely. So, for example, it's just as likely that I would finish lecture in 47 to 48 minutes as I would in 53 to 54 minutes. So let's look at part A. So we want to create a graph of the probability density function. So what we're going to do is we're going to scale it from 45 to 60 on the horizontal axis. And then since it's a uniform distribution, we're going to draw it as a rectangle. Now, on part B, it says the random variable is any number between 45 and 60 inclusive. So the width of the rectangle we would know is 15. So the area under the graph of the probability density function must equal 1. And the area of a rectangle we know is base times height, and it must equal 1. So if we know the base is 15, and we're trying to figure out the height must be 1/15 in order to make that area computation work out. So if I go back to the y-axis, I can say the height of our graph is 1/15. So this allows us to find the probability, such as on example C, it says find the probability that a lecture will end between 50 and 54 minutes. So I'm going to draw what this would look like as a visual in green. So I'm going to cut off this section of the rectangle. And so since the total area of the red rectangle is 1, if I can find the area of this green rectangle, this would tell me the probability I would finish lecture between 50 and 54 minutes. So area of a rectangle, base times height. So we know the base is 4, because 54 minus 50 is equal to 4. And the height of that probability density function is 1/15. So 4 times 1 over 15 is about 0.2667. So there's almost a 27% chance I'll finish lecture between 50 and 54 minutes. Which any 4-minute interval would be that same probability. So if it was between 54 and 58 minutes, same probability. Okay, so let's look at example 2. So on example 2, imagine a bedroom maintains a temperature between 60 degrees and 80 degrees Fahrenheit. Okay, and the temperature at any given time is equally likely within this range. Okay, so this implies we're dealing with a uniform probability density function. So we're going to let the random variable x represent the temperature of the room at any given time. So on the x-axis, for this part A, I mean, even for part B, these graphs are going to look the same. So they're going to be scaled from 60 to 80 on the x-axis. Keep in mind the total area under this rectangle is 1, because we're associating it with a probability. And we know the probability of the temperature being between 60 degrees and 80 degrees Fahrenheit is 100%. It's got to be between those two temperatures. So since the width of this rectangle is 20, the height must be 1/20, because we know 1/20 times 20 would equal our total area of 1. I'm going to change this problem up. It says 64 to 72. I'm going to change it to be 70 degrees Fahrenheit. So, okay, so it says, what is the probability of the temperature? what is the probability the temperature will be between 64 degrees Fahrenheit and 70 degrees Fahrenheit? So same as the last problem, I'm going to try to visualize this. So 64, 70, we're going to cut off that section of rectangle and try to find the area of this green rectangle. This will be the probability that the room is between those two temperatures. So again, base times height. So the base we know is 6, because 70 minus 64 is 6. And the height of our density function is 1 over 20. So if we do 6 times 120 over 1 over 20, we will get 0.3. So 30% probability. Okay, moving on to part B. There is a 40% probability that the temperature is between 60 degrees Fahrenheit and some other temperature. Okay, so same rectangle, same uniform distribution, same height. Okay, so we know that the rectangle will be somewhere between 60 degrees and some other number. So I'm going to cut off this section of the rectangle closer to 60 degrees. And I know this area should be 0.4 because of that probability of 40%. So we need to figure out what this base length is for this rectangle. So base times our known height of 1 over 20 should equal 0.4. So if we multiply both sides by 20 or even divide by 1 over 20, we'll get the base is 8, right? So again, we could do like 0.4 times 20 to get it to be 8. So if the base is 8 in length, this temperature here should be 68 degrees Fahrenheit. Okay, so next we're looking at histograms, which we saw back in chapter 2. So consider the histograms below, which represent the IQ scores of 10,000 randomly selected adults. Notice that as the class width of the histogram decreases, the histogram becomes closely approximated by that smooth curve right here. So just observe, all three of these histograms represent the same data, and the class width looks about like 25 on that first graph, 10 on the second graph, maybe 5 on the last graph. So as the class width decreases, we're also creating more classes to accommodate all the data. And you'll notice as we do create this smooth curve that approximates this histogram. So you can imagine if we created an infinite number of classes, it would get even closer to this smooth curve. So we call this a model, and we call it the normal curve. So because it's a model, it's very good at approximating data that is bell-shaped. So a continuous random variable is normally distributed, or said to have a normal probability distribution, if the distribution is bell-shaped. So we're going to say that bell-shaped and normal distributions are synonymous from here on out. So in that graphic in the box, this is a histogram of SAT score data, and we can see the smooth curve can approximate this distribution. One thing to know about normal curves is that even though they seem to stop at the ends, normal curves are implied to go on to negative infinity and infinity forever, which will be helpful in future sections of this chapter. So we're going to recall a lot of things about bell-shaped data. One thing is that right in the center of bell-shaped distributions is the mean, median, and mode. But we rely on the mean typically for our calculations. Okay, so we're going to look at some transformations of some normal curves. So on example 3, it says in figure A, it shows only a change in mu, the mean. Right, so we can see the standard deviation doesn't change. So as the mean increases from 0 to 3, the curve is shifting right. Right, which means if it was to decrease, like from 3 to 0, it would shift left. And figure B shows a change only in sigma, the standard deviation. So we can see the mean's not changing. So on this first one right here, so as sigma, the standard deviation, blank, the normal curve becomes flatter and more spread out. So here, we're looking to put increases. So as the standard deviation increases, right, so for that red graph to the blue graph, we can see it becomes more flat, which is to be anticipated because we know sigma, the standard deviation, is a measure of the spread of the data. So as you increase the spread, the graph should become flatter. Okay? So the other way, so as sigma, the standard deviation, decreases, we would expect the normal curve to become taller and thinner. We're looking back at chapter 3 information about a bell curve here. So just quick recall of the important things. The mean, median, and mode all lie within the center of the distribution. The new important thing about the bell curve is that the total area under the curve equals 1 because we're associating the area with the probability of our random variables. The other most important things is remembering that 68% of your data lies within 1 standard deviation, 95% lies within 2 standard deviations, and almost all the data, 99.7%, lies within 3 standard deviations of a bell-shaped distribution. Okay, so example 4, the heights, typically heights are something that are normally distributed. So the heights of 10-year-old males are normally distributed. Hence, we can use the bell curve down below to represent the data. So the mean is 55.9 inches and the standard deviation of 5.7 inches. So the mean goes right in the middle on the x-axis label. And then to figure out 1 standard deviation above the mean, we just add on 5.7, which gets us 61.1. And 1 standard deviation, so subtract 55.9 minus 5.7 to get us 50.2. To represent 1 standard deviation below the mean. So repeat this for figuring out 2 standard deviations above and below the mean, and once more for 3 standard deviations above and below the mean to fill out these parameters. Okay, so part B, shade the region that represents the proportion of 10-year-old males who are less than 46.5 inches. Okay, so that'd be about right here. We're just trying to estimate it. I'm just going to label it up top because I'm running out of room on the horizontal axis. And since we're looking at the proportion of less than, we want to shade to the left of that value. So there's a couple of interpretations for this shaded region. So on part C, it says, suppose the area under the normal curve to the left of 46.5 inches is 0.0496. So we want to provide 2 interpretations for this result. So the 2 interpretations when we're shading an area under a distribution curve is we can relate it to proportion of that population that we're looking at, or we can see it as the probability of randomly selecting someone from that population. So first interpretation, the proportion of 10-year-old males with a height of less than 46.5 inches is that corresponding area it gave us, which in the next chapter we'll talk about how do we even get that number it gave us. And then the probability of random selecting a 10-year-old male with a height of less than 46.5 inches is 0.0496. So just 2 different interpretations for that area. All right, so example 5. The lengths of human pregnancies are normally distributed, so hence we can look at a bell curve for the data, with a mean of 266 and a standard deviation of 16 days. So the figure represents the normal curve. The area between 230 days and 260 days is 0.3416. So provide 1 interpretation of this area. So just like the previous example, we can represent this area under the curve between those 2 values as a proportion of that population. So the proportion of human pregnancies that lasts between 230 days and 260 days is that corresponding area of 0.3416.